Welcome. This module will explain decision tree classifiers and how they are constructed. This module is by Matthew Wallace, Carmen Haseltine, and Atticus Sharp as a final project for ECE532 at the University of Wisconsin-Madison. Let's begin with a basic overview. A decision tree is simply a sequence of yes or no questions that split an input set into purer and purer subsets. Ideally, this continues until the data is entirely separated. As a toy example, consider the tree on the right. We have an input set of writing tools. The first question targets pencils and splits the input set into pencils and everything else. This immediately classifies all pencils, but we'll need another question to delineate between markers and pens. After asking the second question, we've successfully separated all input classes. From this, we see that decision trees operate in an intuitive way, but how do we construct them? To do so, we need good questions, and we need to know when to ask those questions. Before diving into a decision tree training algorithm, let's break down their anatomy. All questions reside in decision nodes, and all labeled outputs reside in the leaves of the decision tree. Each decision node corresponds to an input feature, and each leaf corresponds to an output class. Note that for binary classification, we can have many leaves that assign the same label. The tree is hierarchically constructed, meaning the most important questions are asked first. Therefore, the root node contains the question that does the best job of classification. In this example, the tree predicts whether a person will bike or drive to class. The table shows the training data, and I've highlighted the cases where using only one feature would lead to misclassification. This illustrates the importance of each question and explains why the questions appear in this order. Whether the person is running late is the best indicator of whether they'll bike or drive, followed by the chance of precipitation, and finally, the temperature. From the previous slide, it's clear that putting the questions in the correct order plays a very important role in decision tree construction. By asking the best questions first, the data is partitioned the most efficiently and accurately. To order the questions, we'll use information gain to evaluate how good the questions are. Information gain is the reduction in entropy achieved by partitioning the input set with the question. Here we can think of entropy as uncertainty. So loosely speaking, information gain describes how much we learn from each question. By calculating the information gain for each question, we can compare the questions. The question with the highest information gain is the best question. Information gain is calculated using this equation. The terms in this equation are entropies, and entropy will be explained momentarily. From a high level, we can think of this term as the starting uncertainty of our set, before partitioning it with a question. And we can think of this term as the uncertainty of the set after partitioning it with a question. By subtracting the partitioned uncertainty from the unpartitioned uncertainty, we obtain the amount of information gained by asking the question. Entropy forms the foundation for information gain. Entropy is information content, and it's typically expressed in bits of information. For our purposes, we'll think of entropy as the amount of disorder in a set. And we'll think of conditional entropy as the amount of disorder in a set after partitioning it with a question. These entropies are essential for calculating information gain, since the information gain is simply conditional entropy subtracted from an entropy. Again, this term is the disorder of the starting set, and this term is the disorder of the starting set given that we know the answer to this question. Entropy is simply a sum over a discrete random variable's probability mass function. For single variable entropy, we sum over x, where P of x is the probability of x happening. For conditional entropy, we sum over x and y. Here, P of xy is the probability of x and y happening at the same time. Note that the conditional entropy equation can be written in many different forms. This is just one common way of writing it. Now that we have the necessary tools, let's build a decision tree. First, we calculate the entropy of the training labels. We see that the person biked 2/8 of the time and drove 6/8 of the time. By simply plugging these values into the entropy formula, we obtain the entropy of the input set. Next, we'll compute the information gain for each question. Let's walk through this. For the first question, the answer is no 4/8 of the time. This corresponds to these values in the equation. The answer to the first question is yes 4/8 of the time as well. That corresponds to these values in the equation. In other words, P of y has two values, 4/8 and 4/8. One value for no in red and one value for yes in green. Next, let's consider the P of xy terms in the conditional entropy equation. There are 4 cases here. The first is when the answer to the first question is no and the person biked. And we see this happened 2 of the 8 times, corresponding to these values in the equation. Second is when the answer to the question is no and the person drove. Again, we see this occurred 2 of the 8 times, corresponding to these values in the equation. Third is when the answer to the question is yes and the person biked. This never happened. In fact, this is a special case where this term is undefined. Here, we just take the limit of the term which evaluates to 0. Finally, the fourth case is when the answer to the question is yes and the person drove, which happened 4/8 of the time, corresponding to these values in the equation. The conditional entropy evaluates to 0.5 bits, which is then subtracted from 0.811 to obtain the information gain, which is 0.311 bits. After repeating this process for all the questions, we can compare their information gains. We see that none of the questions have 0 information gain, and that the best question is the first question. The first question then becomes the root node. Now we have 2 branches, and we'll need to repeat the process for each of those to keep building the tree. Let's focus on the left branch of the tree. We'll repeat step 1 for the boxed node, except we'll only use the input data that gets passed down the left branch. So we're ignoring the blacked out entries. For this subset, the person drove every single time. So the entropy is 0. And for step 2, all the information gains are 0. As a rule, 0 set entropy implies 0 information gain. And whenever we have 0 information gain, we need to create a leaf. Here, the leaf assigns a value based on the majority vote of this subset. Since 4 out of 4 labels in this subset are drove, this leaf will predict drive. Next, we'll repeat this process for the node on the right branch. Here, we'll use the other subset of input data partitioned by the root node. Again, we'll calculate the entropy for this subset of training labels. In this case, the entropy is 1 bit. Next, we'll calculate the information gain for each question then compare them. Notice that in this case, we have a tie between question 2 and question 3. Their information gains are equal. A simple tiebreaker is simply to pick the question whose information gain we calculated first. Therefore, question 2 is the winner, so it will become the next decision node on the right branch. Finally, we'll move on to step 4. We'll just keep iterating through this process until no new nodes are created. The information gain for all questions will eventually be 0, so all the branches of the tree will be terminated with leaves. Next, we'll focus on formulating the questions. To iteratively split the input set, decision trees require a discrete set of node outcomes. In other words, if we have a contiguous feature like temperature, we'll need to ask a question about it that only has a few possible answers. This is often done with thresholding, where we use a threshold alpha to split the input set into 2 subsets. For example, consider temperature with a threshold of 20 degrees. We simply use the step function to split its contiguous temperatures into 2 classes: temperatures greater than 20 degrees and temperatures less than or equal to 20 degrees. Binary features do not require a threshold since they already contain 2 classes. The only questions we can ask about binary features are already yes or no questions. Again, it's only when the feature contains contiguous data that we need to threshold or use some other method. But how do we choose the threshold alpha? Here's a basic algorithm for choosing a question threshold alpha. To be clear, there are many more sophisticated ways to form questions for contiguous features. This is just a common one. To perform this algorithm, we're simply going to take all the values for the feature in question. We then try each of these values as the threshold, and the one that produces the best information gain across the entire input set is the threshold we'll use for the question about that feature. Overfitting is a common problem in decision trees. If cross-validation indicates overfitting, the tree should be pruned. For post-pruning, we first construct the whole tree. Then, decision nodes with information gain that is too low are turned into leaves. For example, if this temperature decision node had an information gain below the threshold lambda, we would simply get rid of it. We would turn it into a leaf. This will make the model more generalizable. And of course, we can use cross-validation to optimize the pruning parameter lambda. After watching this video, you should be able to understand the following high-level algorithm. First, we formulate questions by thresholding any contiguous features. Then, we hierarchically construct the decision tree using information gain. Finally, if the tree exhibits overfitting when we're checking it with cross-validation, we should prune the decision tree. This will increase the generality of the model. For the pros of decision trees, they are simple and easy to understand. They can separate non-linearly separable classes, which is something that a simple linear classifier cannot do. They also exhibit implicit feature selection, so unimportant features will not be used in the decision tree, and we can remove them from the model. For cons, there is a high chance of overfitting, and what we can do with pruning tends to become limited. Decision trees also do not scale well. For many features, generating a good model will be very difficult. Also, small changes in data can result in large structural changes to the constructed tree. So training the tree with slightly different subsets of the training data may result in very different trees. Thanks for watching.